review without proof a couple theorems that we know and do an example, but then we're going to move on to what happens if we're interested in something that is not a rectangle. Okay, so let's just remember these two results. Okay, if f is bounded function on a rectangle, okay, then another way of checking its integrable, aside from using the definition, f is integrable if and only if, for all epsilon bigger than 0, we can find a partition of our rectangle such that on this particular partition, the upper sum and the lower sum stay close together. Okay, so for example, when we did an example using the definition, we did an example with linear, and we kind of noticed several times throughout that we were quite happy it was a linear example. Let's do something nonlinear now. So let us show that the function x squared y is integrable on the particular rectangle 0, 1 crossed 0, 1. All right, this would be doable, but a headache if you have to do any general partition and locate your xj, any general point in there. There would be a lot to keep track of, and it wouldn't decouple so nicely. But in this case, we're in luck. We just need to find any particular partition, so we're going to do whatever is easiest for us. So we'll pick an epsilon. And then we're going to just build uniform partitions of both of these, and we can use the same uniform partition. So let's let p tilde be this partition, just a uniform partition. Okay, n is the number of subintervals that we have. So n is going to be related to h this way. Okay, so we do a uniform partition of each dimension, and then that gives us a uniform partition of our overall rectangle. So p is p tilde cross p tilde is a nice partition of our rectangle. All right, and now again, we're in luck. We don't have to look at every possible location of these. We had these Cij and eta aj last time. We just have to try to find the supremum of f and the infimum of f in each little box. Okay, so if mij is supposed to be the supremum of our function f of x, where x, let's say f of xy actually, okay, where x is in the ith subinterval, and y is in the jth subinterval. Well, now again, we're not looking at some sort of generic Cij. We can figure out exactly where this is not just, it doesn't just have a supremum, it actually attains a maximum in this case, right? So this is a monotonically increasing function in both x and y on our particular domain, so we just have to let x and y be as big as possible. Okay, so this will just be obtained with xi squared times yj. And we have very simple expressions for these. So this is just going to be I squared j h cubed. All right, and similarly, we can take the infimum, and we have to go to the left, and we get I minus 1 squared j minus 1 h cubed. All right, so now we're in business. We can go ahead and try to compute our upper sums and lower sums. So our upper sum is going to be, we have to sum over all of these little rectangles. So we'll go from I from 1 to n and also from j to 1 to n. We need this quantity, this supremum. And then we have to multiply by the volume of our rectangle. And of course, life is good. All the rectangles have precisely the same volume. So this is just another h squared. All right, and despite the nonlinearity, things are actually going to decouple very nicely for us here. Right? And that's because we were able to do things simply. Otherwise, we would have, well, we try to pin things at the midpoint, but it would be stuck in a nonlinear function plus leftovers, and this is all stuck in this nonlinear function. It would be a lot messier to try to keep track of. Okay, so this just works out to, well, we got an h to the 5th. Then we have to sum I squareds, and we have to sum the j's. We say, we've seen sums like this before. We go look up the formula. You don't have to memorize them. If you need these formulas on a test, I give them to you. And we say, great, the sum of the first n squared numbers is precisely n plus 1, 2n plus 1 divided by 6. And the sum of the first n whole numbers is n plus 1 over 2. Okay, so we've got an exact sum. We can simplify this a little bit, right? This exact sum is not going to be the exact value of our integral, but we can still kind of guess the value of the integral from this by looking at it a little more closely. And the reason we can do that is because we have this relationship between n and h. So everywhere I see an n times h, I make that 1. So what I'm going to do is multiply these h's through. I have 5 terms here, conveniently, so I'll stick 1h in each term. All right, and what am I going to get? I'm going to get n times h is 1 here. nh plus h, so I'll get a 1 plus h. All right, 2nh plus h, so that's 2 plus h. All right, nh, that's 1 again. And then another 1 plus h, so that's squared, divided by 12. Okay, and we can, of course, multiply that out if we want to, and that should be 2 plus 5h plus 4h squared plus h cubed divided by 12. All right, so we got to get kind of a guesstimate of the value of the integral from here. We've got this leading order term, 1/6, and everything else is small. Everything else depends on these h's, and as we refine our partition, h goes to 0, and we think those will go away. So this is the upper sum. We could play the same game with the lower sum. That's not any different. It's just that we have I minus 1s and j minus 1s here. So instead of summing over the first n integers, it's really just the first n minus 1, with the first term being 0. So same game with that. I'll just give you the punchline, which is something that's very similar. All right, leads the same way. That's good. And then we just have some sign alternating here. All right, and what do we need to do? We need to look at the difference between these two things. So if we take the difference between them, well, we're going to get some cancellations, right? So first term cancels, second terms add together, so we're going to get 5, 6h. The 4h squareds cancel. The h cubes combine, so we get 2h cubed over 12. We want to make this less than epsilon. And I guess an easy simplification we can do here is that h is at most 1, right? I mean, our domain length is only 1, so h is not bigger than that. And that means that h to any power is going to be less than or equal to h. So I could do something like this. Okay, that works, since h is certainly less than or equal to 1. And we can certainly make this less than epsilon by refining our partition enough. So this is always going to be less than epsilon as long as we do the obvious thing and take h less than epsilon. Right, and that's all we need to check. So this nonlinear example was easier to do than the linear case from last time because we used a better characterization. Better, I don't like to use the word better here. We used a characterization that is more suitable for this problem. Okay, so f is integrable on this particular rectangle. And we can take a pretty good guess at what the value of the integral is. Right, all the Riemann sums are going to be squished between this quantity and this quantity. And since these both limit to 1/6, the Riemann sums are also going to get close to 1/6. All right, questions there? All right, the other result that I'm going to just write down without proof is, and we already talked about this a little bit last class, continuous functions are integrable. And I don't need to prove this because the proof is identical to what it was in 1D. All right, continuity just means the function values can't change too much on each subinterval, and so we can always force things less than epsilon. So if f is continuous on a rectangular, then it's integrable. Okay, so that's rectangles. We kind of know everything we want to know about integrating on rectangles. Let's try to do something more interesting. We want to integrate over a more general regions. So let's call this set S. So how to integrate over regions. We want to do this integral. All right, as always, I want to take advantage of everything we know so far, right? I'm not trying to reinvent things, I'm just trying to generalize a little bit from the rectangle, but hopefully use the same, more or less the same definitions. So what I'd really like to do is turn this into a problem of integrating over a rectangle. That's what I want to do. And then everything we know about rectangles holds. Any thoughts? How do I turn this into a rectangle problem? Yeah?
Could you maybe do like change of variables or something?
Okay, so change of variables maybe. Now how easy that's going to be is going to highly depend on this guy. Let's think simpler. Also, we don't know how to do change of variables yet. Yeah?
We can draw rectangles inside.
We could draw rectangles where?
Inside S.
You could draw rectangles inside S and try to integrate over a whole bunch of rectangles inside S. Add them up. Okay, that could work. Let's think simpler. You're very close. There was one word that was off in what you suggested. Yeah? Let's draw a rectangle outside S. I'm going to turn this into a problem of integrating over a single rectangle, and then my definition holds. I'm not taking a limit of little rectangles. So I'm going to do this. I'm going to draw a box around this, and I'm going to introduce some new function. And inside of here, it agrees with my usual function. Outside of here, I don't want to add up any other extra stuff. So outside of here, it's going to be 0. And now I'm going to integrate this new function over a rectangle. Now my new function is probably not continuous. I mean, it could be if this thing decays to 0 at the boundary. It's not necessarily continuous, but we know we don't need continuity in order to integrate. It's just a nice thing to have. So we're going to write down a rectangle over this, and then we're going to think about, you know, what can we get out of this? So say we have a nice function that's continuous in here. Does that mean the integral exists? When does it exist? Okay, but this is my starting point for defining. All right. So let's suppose that f is a bounded function, and it's defined on a bounded set S. It has to be bounded because otherwise I can't draw a rectangle around it. All right, let's define this new function. All right, exactly the way we drew it there. So it's going to agree with our original function in our original set, and it's going to be 0 otherwise. All right, now we draw a rectangle around this set. This is bounded, so we can certainly draw a rectangle around it. So let's let R be any rectangle in Rn that contains our original set. Okay, then we're going to define the integral like so. So the integral of our function over this complicated region is simply the integral of our modified function over our rectangle. And that we already know exactly how we should define. And we know some tricks now for checking if that integral exists. So we'll define it like this: if the integral exists. Questions on the definition? Make sense? It's the easiest thing we could do here. You know, the idea of trying to draw lots of rectangles to stay inside of here, that would probably lead to the equivalent thing, but you know, this is kind of easy to write down. This also gives us a way of talking about the volume of a complicated set. Right, volume of a rectangle was kind of easy, just multiply the side lengths. But now we can start thinking about how to compute the volume of a crazier set like this. And the way we would do that, how would we do that? Yeah?
We make the original function equal to 1 instead of 7?
Exactly. We make the original function equal to 1, and we just integrate 1 over here, and we'd expect that to give us back the volume. It certainly gives us back the volume for a rectangle, which is always an important sanity check. Do these definitions work on the easy cases? Okay, so we're going to also define the volume or the content this way. So if S is bounded, then we're going to define the volume or content of S just to be the integral over this set we care about of the function 1. If this integral exists, and this is going to be our sticking point here. We're definitely not integrating a continuous function at this point, right? Now we have something that is equal to 1 in here, and then it drops off to 0 instantly out here. It's not continuous. So we have a way to define this integral, but we don't at this stage have a way to say, yes, this integral really exists. Now our experience is mostly 1D. There are plenty of discontinuous functions in 1D that you can integrate. There are also some pathological examples of functions in 1D that we can't integrate. So we want to know which category are we in, or what has to be true about S for us to be able to do this integral. This is going to be the key for us. Yes, we have a function that's discontinuous. It's not like it's discontinuous everywhere. I mean, some of the pathological examples that we did in 1D were like functions that were, everywhere bouncing between 0 and 1, and then we just throw up our hands and say we can't do this using Riemann integrals. That's not happening here. So, I mean, there are infinitely many places where this is discontinuous, but somehow, although it's infinite, it's a small infinite. It's a small set, right? So we're in 2D. We have volume. This curve has no volume, right? It's just like a line. It takes up no space. So this is going to be our saving grace, is that as long as we have this boundary taking up no space, we're going to be able to do it. We're going to be able to say, most places our function is nice. We have some places where our function is horrible, and we don't quite know what to do with it. But that happens in such a small region that we can surrounded by little rectangles that have arbitrarily small volume and kind of force them to be less than epsilon. That's going to be the game here, is split up our domain into rectangles where f is nice. Inside here f is nice, outside here f is nice. And rectangles where bad things happen, but there aren't so many of those rectangles. Yeah?
Does this hold for non-countable set of points?
Does it hold for what?
Non-countable set of points.
Non-countable set of points? So, yeah, this doesn't hold for every set S. We'll try to clarify exactly what we think is going on here, but yes, you could have pathological sets where this is not going to hold, and the problem is precisely when the boundary starts going crazy and trying to take up space. If you have a boundary that's wrapping around and around and around and around, and all of a sudden the boundary starts filling up volume, which you don't want it to do, that's where you're going to run into problems. Okay, so first, I want to clarify what I mean by the boundary doesn't take up any volume. So we're going to come up with this concept of a set of zero volume or zero content. And then we're going to hope that the sets we want to integrate over have boundaries that are in this category. Okay, so we want to say, what does it mean for a set to have zero content or zero volume? All right, let's have a picture to go along with it. So we want something that kind of jives with the concept of the Riemann integral that we're working with. The Riemann integral is all based on, we divide our setup into lots of little rectangles, right? And then what do? If we're integrating the function 1, we add up the volume of these rectangles. So that's what we really want to be doing here. We want to cover this thing in lots of little rectangles. I'm going to not make them too little, just, that's not a good rectangle. In the interest of drawing this in a finite amount of time. I need another little rectangle here. And then what we're going to hope is that if we add up the volume of these rectangles, it's small. And in fact, that we can add up the volume and make that volume as small as we like, less than any epsilon that we care to look at. So this is what I'm going to say. You're going to give me a tolerance, and you're going to say, I want to check that the volume of the set is less than that tolerance. And if the volume of this boundary is less than any epsilon, then we're going to say the volume is 0. Okay, so we do exactly this. You know, in each rectangle, I know how to integrate, and I know that the value of the integral is bounded by the volume of this little rectangle. So that means that the total integral over the union of all of these things is at most the total volume of all these rectangles. If that's less than epsilon, then something that's contained in here is also taking up less than epsilon space. So if for every epsilon greater than 0, we're going to say there exists a finite set of rectangles R1 to Rm. Okay, such that our set is contained in these. and the total volume on both of these rectangles is less than epsilon. All right, this is okay? Happy with this? All right, so let's think of an example where this would happen. So let's suppose that we have a curve in R2 that we can describe as the graph of a function. Okay, so let me clarify this. Let's suppose we have a function that is continuous on a bounded interval. Okay, now the set I'm going to be interested in is the set of points that lie on this curve. Okay, so S is going to be the set of all points of the form, or xy, so the points in R2, we're interpreting them in R2, okay, such that x is between a and b, and y is equal to f of x. Okay, so it's just, okay, here's a, here's b, I have my function f, and my curve S, my set S is simply all the points that lie on this curve. And as this is a continuous curve, continuous function, it's not like trying to blow up somewhere, extend out to infinity, which could be a problem for us. It's reasonable to think that maybe we can cover this in a lot of really tiny rectangles that ultimately don't really take up space. But let's check. All right, so let's show that this has zero content. All right, so we need an epsilon, the usual place that we start almost every proof. We think it's probably important that f is continuous. I think it's probably important, because if f was not continuous, I mean, it might be allowed to blow up or something, and all of a sudden the curve is getting infinitely long. This might be a problem. It matters that f is continuous, so since that matters, we should write down what that means for f to be continuous. The usual thing. We see the words, we write down what they mean. So we have f is continuous on this closed bounded interval, a compact interval. So continuity becomes uniform continuity on a compact set. So what does it mean? It means there exists this delta such that as long as the x values don't change by more than delta, the f values don't change by more than epsilon, right? That's continuity. All right, so let's write down what this means precisely. F is continuous on a compact interval. So uniformly continuous. All right, so once again, I write down what these words mean. There exists some delta greater than 0, such that if x minus y is less than delta in absolute value, then f of x minus f of y is less than epsilon. All right, now I have to use this fact somehow to build up a set of rectangles. And I've got to work out the volume of each of these rectangles. Okay, so somehow I'm going to have to come up with a rectangle, and I have to decide how big this rectangle should be. Well, I'm going to use continuity to decide on the volume of the rectangle, right? So if I decide how much I'm going to vary in the x direction, continuity tells me how much I'm allowed to vary in the y direction. That gives me a bound on my volume of my rectangle. Right, so ideally for each rectangle, I want the base to be less than delta, right? Because if the base is less than delta, then I know my function is varying by at most epsilon. And that's going to give me a bound on the volume of my rectangle, and let me compute a bound on the volume of my rectangle. And the volume of the rectangles are things that I definitely need to do. All right, so what I'm going to do is I'm going to chop this domain up. I'm going to partition it. All right, and I'm going to partition it just in a uniform way because why be more complicated than we need to be. And I know exactly what is going to influence the size of my partition. This delta is going to influence the size of my partition. Okay, so let's let P be a uniform partition of A to B with norm less than delta. All right, so P is going to look like this. P is going to be points of the form A plus I times H. I going from 0 to n. And H equals 1 over n is chosen to be less than delta. All right, so I'm going to use this to build a rectangle. All right, so this component of the rectangle is kind of easy, right? Our partition has decided what the base of our rectangles are going to be. So let's build rectangles. So the ith rectangle, well, along its base, we're just going to go from xi minus 1 to xi. And now we got to give it a height. And we got to be careful here. We need to make sure that our function stays in this rectangle. It's not allowed to come out and come back in, right?
Should that be a b minus a over n, or?
That should probably be a b minus a over n. Yes, thanks. Okay, so I guess what height should my rectangle have?
f of xi.
What's that?
F of xi minus 1.
F of xi minus 1. That's a good place to start. And then, well, my function could go up from here or it could go down from here. I don't know which, right? So I'm going to say if my function goes down from here, there's only so far it can go down, right? It goes down by at most epsilon. And it also goes up by at most epsilon. So what I'm going to do is take it to go down by epsilon and also up by epsilon. And that ensures that everything that my function is totally sandwiched in here. Maybe overkill, maybe my function is really flat here, I don't know. But this will do it. So I'm going to take, indeed, f of xi minus 1 minus epsilon, f of xi minus 1 plus epsilon. And now there's two things that I have to check. I have to check that my set is contained in the union of all of these rectangles. Now, we've designed these rectangles in a pretty careful way, so that should happen. And then we also have to check that the total volume of all of these rectangles can be made as small as we like. All right, so we need to do two things. That our set, did I call it S? S. S is contained in the union of all of these rectangles. Okay, so the general way to do that is you pick a point in S, any point, and you show that it also lies in one of these rectangles. So let's choose any point. All right, here's how points in S are defined. So X is certainly between A and B, and that means it lies in one of these subintervals. Partition, by definition, encompasses all of that. So X belongs to AB. That means it fits in our partition somewhere. All right, and now, so we're in one of these. Now we just have to check that our function value hasn't jumped outside of the rectangle. Okay, so what do we know? Well, what is this quantity equal to? Or what's the worst it could be? Yeah. What's that? Yeah, it's not more than delta, right? It's at worst h, and h is less than delta. Okay, because these guys are in the same subinterval. And that means, by continuity, that f of x minus f of xi minus 1 is less than epsilon. And f of x is precisely going to correspond to our y value. That's the only thing the y value is allowed to be, is f of x. Okay, so that means that indeed y minus f of xi minus 1 is less than epsilon. And that means y is going to fit into this interval. Right, this interval includes everything up to that is a distance up to epsilon away from our reference point. So indeed we have, as we expected, x, y belongs to a particular rectangle, and so it belongs to the union of all of them. This is not a surprising conclusion. I mean, we manufactured our rectangles to make sure this would happen, so this is just a quick sanity check along the way. Now, the other bigger thing we have to check is that actually the total volume of these rectangles stays small. Maybe not totally obvious, because as we refine our partition, it means we have more and more and more of these rectangles to add up. So they better be getting smaller in size fast enough to overwhelm the fact that there's a lot of them. So claim 2 is that the volume of all of these is less than something. Less than something that goes to 0. All right, we can work out the volume of rectangles. That's not hard to do. So V of our I is going to be, all right, so the base times the height. All right, this is equal to h. And this is equal to 2 epsilon. Now we need to add them up. Okay, so how many rectangles are there? There are n rectangles, which means this should probably have been an n here. Okay, so let's sum them up. Okay, so we're going to sum up all of this stuff. Well, there's no i's in here, so it's just n times this quantity. Okay, and we know what n times h is. It's just the total width of our domain. So this is 2 times b minus a times epsilon. And that's good enough, right? We can make this as small as we want by taking epsilon smaller and smaller, right? Everything out in front is just a constant. None of this depends on how we've done our partition. So we can say, great, actually our set has 0 content, as we hoped. Questions?
So, I guess we're not fixing epsilon here.
So, I mean, we started by, which is erased now, by picking an epsilon.
Yeah.
Now, in any of these proofs that are where the definition says I can make less than epsilon, it's really just less than something that goes to 0 with epsilon.
Okay.
So, maybe I'm fixing my epsilon tilde, if you like. I'm fixing this, and then I'm saying, well, based on my tolerance epsilon tilde, I can pick an epsilon that agrees with that. That alternate epsilon gives me a delta. So you can always reword it, and I could have picked these quantities differently. I could have said, let's try to make this less than epsilon over b minus a here, and it would have, you can reverse engineer it to come out as an epsilon, which looks prettier, but you have to kind of go through the proof twice to do it. You have to know the answer ahead of time to do it. So I can present it to you that way, and it looks pretty at the end, but then along the way you're going, why are you making these choices? Or I can do it like this, which is how I would do it in the real world. All right, so what was the point of this? The point was to be able to integrate over more complicated regions as long as the boundary of our regions didn't get too out of control. So this is our big result that we want. Let's suppose that f is bounded on a rectangle. Okay, and it's continuous everywhere except on a set of 0 content. Okay, so as long as we've restricted our discontinuities to a small number of points in some sets, we can do this. We can say then f is indeed integrable. Okay, so this is a generic function, but this would encompass the case where we say f is whatever it is in S and it's 0 outside S.